Go ahead.
So, hey, yeah, my name's Sam, and I'm a second year a PhD student at the Cardiff University, rather. And I'm going to present to you what I've been up to for a bit the last year and a half, which is to do with constraining GRB jet structure using joint GRB and gravitational wave observations. Oh, that's not working. There we go. So first off, just to preface, what's a gamma ray burst? So these are the result of a compact remnant creating a torus of matter left behind by whatever event that formed it. And these are these large jets sort of aligned down the rotation axes on both ends of these remnants. We're going to be more specifically focused on short GRBs in this talk. These are usually shorter than 2 seconds. Until 2017 and the observation of our first joint GRB gravitational wave detection, which was the joint detection of both GW-170817 and GRB-170817A, there was actually no direct evidence for what the progenitors of these was. Now, from GW-170817, it was possible to figure out that this was actually due to the merger of a binary neutron star system. And you can see on this plot down at the bottom here, you can see this characteristic chirp of the gravitational wave signal, and then about 2 seconds later, the beginning of the GRB in the Fermi-Lie curve. So GRB-170817A is actually particularly interesting for a specific reason, which is that it's not only a few orders of magnitude closer than any other known SGRB of known redshift, but it's also a number of orders of magnitude more dim than any previously seen. And this dim emission suggests that there is some physical process there that has caused this emission that we've yet to see or understand. And the biggest most focused sort of explanation for this in the community has been structured jets. So what these do is essentially explain this observation as some sort of off-axis observation due to an angle dependence on the luminosity of a GRB jet. So if you take a look at the bottom here, you can see this thing that you see here, this y theta v that's in the box, is what is regarded, which is called a shape function. And you can see here, this is a simple Gaussian model where it's going from 1 to 0 and given some 1 sigma width. Essentially, you're able to apply that to the central luminosity of a GRB in order to produce some sort of angle dependence, depending on what angle you're viewing it at. This theta v, the viewing angle, is also the inclination, which is something more easy to think about. And it's worth noting that the gravitational wave information from 170817 was able to constrain this inclination to around 30 degrees. So we do know that it's off-axis, and that adds a bit of credence to using structured jets. So the goals of my project specifically have been to produce simulations of populations of structured GRBs for a number of different jet parameters. And hopefully by applying observational evidence and constraints to these, narrow down this portion of parameter space which aligns with this observational data. And then hopefully that will not only constrain these jet models, but also provide some information on potential future prospects of observations of joint detections in O4 and beyond. So with regards to constraining parameters, there are 2 parameters that are of greatest interest when producing these jet models, and those are theta d here, which is the 1 sigma width of these Gaussian jets, and there is L naught, which is the low luminosity cutoff of the GRB luminosity function. So what is done is that produce this region of 2D space where they're bounded by theta d and L naught, and then produce simulations within that space for all of the different combinations of jet parameters that could exist within that. These sources are all considered as binary neutron stars. There's actually a lot of considerations that go into that, and I would tell you about them, but I fear that would take up a lot of time. So if people wonder, then I can absolutely go over those. But basically, across these regions, we want to find the region which matches all observational constraints and focus in on that. So the first thing that we consider is the matching the rates of both GRBs and gravitational wave observations. So this is constrained by both the CBC rate, which is actually baked into the generation of all of these, the systems within the simulations, and also the Fermi rate, which is the rate at which the Fermi GBM observes GRBs per year. It's worth noting on all of these plots, actually, that all of these individual points in this parameter space take a very long time to actually produce simulations for. So you'll notice that a lot of these plots are a bit splotchy. I'm working with a 10 by 10 grid of values here, but there's no reason why that should change the trends that we're seeing here. It's also worth noting that there are some not ironed out sort of approximations, but they should not dramatically change the results we're seeing here. So just maybe you don't pay attention to the numbers, but the trends should be reliable. So what we see here for matching the Fermi rate, as you can see that essentially it favors either a fairly dim luminosity cutoff with wider jets, or a brighter luminosity cutoff with more beamed jets. And you can sort of reason to yourself that you would only see these wide and dimmer GRBs much closer, but these more beamed and bright GRBs you would see out to a larger range of redshifts, but they wouldn't be as numerous because they need to be aligned to be visible. So you can sort of see why you get this sort of banana shape on the plot here. So next, we matched all of these simulations to the fact that we know that in both O1 and O3, we actually saw no GRBs with a gravitational wave counterpart. So what we do here is we use this probability provided in the O3b GRB paper, which takes into account the exclusion distance of all of previously seen GRBs, as well as a number of other parameters regarding them. And that also considering the simulations that I have here, this shows us that it actually is preferential for the brightest and widest jet model here, that essentially favors not seeing any gravitational wave counterpart, which might seem a bit counterproductive initially, but there's two things to take note of here. First off, actually a large portion of the top part of this plot in theta d is actually fairly irrelevant, because as soon as you get to a particularly wide jet, as you know, the jets are on both ends of the progenitor. So eventually you get they sort of overlap with each other and you don't get this particularly low luminosity segment. But also, essentially you have, so what you have all the way at the top of this are these fairly bright jets that are visible out to a distance far larger than you'd actually be able to see a gravitational wave counterpart. Whereas you're seeing a preference for, or sort of not a preference at the bottom left here, for seeing no counterpart, where we have these sort of dimmer, more beamed jets, because those are more likely to be closer and hence potentially have a GW counterpart that is visible by us. So the final constraint here is matching this to what we know about GRB 170817A. And what we see here, first off, I should mention that actually the non-zero probabilities here do actually stretch across essentially the entire bottom of this plot, but it was impossible for me to find a way to show this without adding a quite ludicrous number of steps on this contour plot. But
yeah, that's your 2-minute warning, Samuel.
But yeah, so we see this clear preference to these more beamed and dimmer jets, where these will be seen almost exclusively nearby, where the gravitational waves from these GRBs would very easily be visible. But actually, you can see that these actually, well, you can't see, but these actually do stretch up to essentially cover the entire luminosity distribution there. Essentially saying that, as long as you have these beam jets, you'll be able to see the full extent of that Gaussian. So you'll be able to see out to the edges of it. Of course, if it's too off axis, it won't be face on and you won't be able to see the gravitational waves. But that's essentially what we're seeing here. So multiplying all of these probabilities together, we get this sort of constrained part of parameter space, which agrees with for the most part, all of these constraints, and we see that it actually definitely favors these tightly beamed jets, but actually favors sort of between the mid-range to the highest limit of these L0 distribution. And again, that's because with these tightly beamed jets, you'll be able to see off to the sort of very edges of that and still retain a GRB of the correct luminosity to match with 17 at 17. And just to finish off, so now we have this sort of constrained bit of parameter space. I'm definitely going to focus in on all of this. And the next step is to really go in to take a look at the gravitational waves that were also generated in these populations and see how the prospects for joint detections change across this part parameter space. Not only has this sort of already shown us sort of constraints on the jet structure, but obviously in doing that, it will allow us to probe the prospects of observations during 04 and beyond. And hopefully in the future, we'll get some more detections and be able to constrain things even further. Thank you.
Brilliant. Thank you very much, Sam. That was really interesting. So while we wait for questions to come in, so do keep posting your questions in the Q&A, by the way. So you said about the jet structure. You use like a Gaussian model for it. And there are other models that you can consider for that as well, or is
there are. So I've shown you the Gaussian model stuff here because that's the stuff that I'm most of the way through, finishing the results off for. But another structure that I'm also putting quite heavy focus on is a power law structure. So that essentially the one that I'm currently working on, it has this it has like a top hat in the middle for this sort of the core jet luminosity. But then beyond that, there is sort of a section beyond that on both sides that drops off in a power law that is defined by a few other parameters that should hopefully be able to be probed in a much similar way as we have with the Gaussian stuff that you've seen here.
Oh, brilliant. Thank you very much.
Thank you.
I can't see any other questions at the moment. Maybe some on the Slack later, but thank you very much, Sam. That was great.